This is a lesson video for 7-2 Day 1. You're going to start with the warm-up sheet that you've been given and come back to the video when you and your table partners have come up in words with what you're being asked to find and then what the solution would look like. Then go ahead and actually calculate and come back and check this against the key in just a minute. Putting good time into this so that you understand what you're finding is critical to your understanding. If you're back then, you're back to look, and again, pause video and slide up and down this. You're back to see what you were finding in good vocabulary, and then that your calculations are accurate. In number 8, we need the natural log of the absolute value of x. Natural logs have a limited input. They can only input values larger than 0. So to ensure that our natural log has a valid domain value, we're limiting x to being positive. In the initial integral, we don't have that information, so we need to include that absolute value, and you'll see that later on again and again when we work with natural log to ensure that our antiderivative is a valid function. Again, pause the video where you need to reread and redo some of these, talk to your table partners. The last thing it asks you to find are the 3 Pythagorean identities. You don't need to memorize all 3. You do need to know that first one. The sine squared plus cosine squared is 1. Each one after that can actually be derived, and I know I've shown some of you this before, but if you know that first one, you could divide to get the other 2, take turns dividing everything in there by one time sine squared and the next time cosine squared, dividing everything in that identity by either sine squared or cosine squared, and you will then have the information you need to come up with the other one. So that one turns into this. Same with taking our initial sine squared plus cosine squared equals 1, divide both sides, each term by cosine squared, and you come up with the last one. As far as notes go, you want to be taking some notes. You want to pause the video. You want to make this worth it so that you're getting the details, but also have the notes, and that would be the first thing I would ask you if you're asking me questions about this, is that you put in your time and can show me some good notes. So in 7-2, we're going to be working on how to handle chain rule when we're looking at antiderivatives. So some basic kind of general stuff to get started, just making sure we know what to call each of the different parts of an indefinite integral. When we're calculating an indefinite integral or evaluating it, we need several things in here. We need an integration symbol to start. We need our integrand, what function are we actually taking the integral of? And we need our variable of integration, that dx, and it needs to match. And we're going to use fundamental theorem that says there is some capital F antiderivative, that a family of them, that plus the constant of integration, is the result of doing that integral. So we call the indefinite integral that antiderivative value that we get. So let's take a look just for one more comparison at definite integrals versus indefinite. You've done some of each now. A definite integral was what you were working on in chapter 6 to get the change in position, change in something, whatever that rate was representing over a specific interval. And so your number should come from either the antiderivative evaluated between 1 and 5 in this case, or the area under the curve y equals 2x between the x-axis and the function from 1 to 5. The limit of your Riemann sum. So many ways we did to get definite integrals, and you have lots of them. We're working with indefinite integrals now, those general solutions, and it's a family of functions that have a common derivative, so the answer to the integral, the indefinite integral of 2x, would be that family of functions x squared plus a constant, whose all have that same derivative. So my indefinite integral is the answer to that. You have used indefinite integrals to solve differential equations. So the connection you want to be able to make from 7-1 to 7-2 is in 7-1, you were solving differential equations. You were given an equation that was a derivative, and you were working to find the solution, the function that's its antiderivative, or the function whose derivative is x squared minus sine x. In 7-2 now, they're asking you to evaluate indefinite integrals. Well, that's how you actually solved your differential equations. They're going to call it evaluating indefinite integrals. which looks like the next step of solving that highlighted yellow equation was to take the integral of both sides. So the answer to this being evaluated is the same thing. This is a huge point to make so that you understand that your skills carry over to two different situations or two different ways of being asked about. So you want to pause video here and make sure that you've got the connection between these two so that you can look back at that. When you do the reading, there are all sorts of properties for working out indefinite integrals. They will go along with the properties you learned for taking derivatives because, again, it's like the way that solving a quadratic equation and solving a square root equation have a lot of commonalities in how you're working back and forth with inverse functions. So if you go back to all your derivative rules, these will seem like the reverse of them. So if I integrate a constant or a multiplier on a function, I can take that multiplier out front and then work with the integral. We saw this with definite integral properties. So as you read through and look through these, I wouldn't write them all down. I would look and write down a handful of them that seem ones I might want to come back to. Ones I might want to come back to, for instance, so there's one about what to do about u to the negative 1, that I recognize that that's natural log's derivative, but since I don't know if my variable u is positive or negative, my natural log can only accept positive values as inputs domain-wise, so its antiderivative needs to be the natural log of the absolute value of u plus a constant. Looking further down, the trig formula ones, those shouldn't surprise you in that's recognizing the antiderivative for a specific derivative. And those are ones that you've worked with a lot before. Exponential and log formulas. The one that I've highlighted here is one sometimes people will say, is this one I need to memorize? And I don't think so, but let's talk through the why it appears the way it does. They're saying that if you had the indefinite integral of something like 3 to the x, that a quick, short way to do this would be 3 to the x all over the natural log of 3 plus a constant. And instead of memorizing that, let's see if we can find out where that came from. I don't know an antiderivative for 3 to the x, but I do know that if I saw 3 to the x times the natural log of 3, just a numeric multiplier in there, that I would know its antiderivative. I would be able to evaluate that. But I can't just throw a multiplier in there without accounting for it. So in other words, if I double something, then I have to take half somewhere in the same calculation to account for it. So if I do that, then I can go ahead and say that my indefinite integral is going to evaluate to 1 over the natural log of 3. I know the antiderivative for this is 3 to the x, and then the final function family would include anything with a constant added, and it's just saying that that's a shortcut to getting there in one step instead of several. So as you look those over, see how they relate to what you know already about derivative rules. You might be asked to verify one of those integral rules. In other words, they're going to use it and show you an example of an indefinite integral being evaluated, the indefinite integral of the natural log of u du, and they're asking you to verify that that is what you should get. So to verify an integral rule, what we're going to do is take the derivative of both sides and show that those are equal. So I'm going to take the derivative with respect to u's because that's the variable of integration here. And on this side, again, I'm going to take the derivative with respect to u because that seems to be the variable on this side. So the derivative of my integral is just the natural log of u. And then on the other side, the derivative of each term in there will need to be taken. So the derivative of this first term is a product. I have to go back to product rule. First term times derivative of the second plus second term times the derivative of the first. Now I'm up to this term, so minus 1 for its derivative, plus 0 for the derivative of the constant. And when I go to clean this up, I'm going to get u over u, or 1, plus the natural log of u, minus 1, which is natural log of u. So I've verified that if I take the derivative on both sides, I do get an equal I do get a true statement that they're equal on both sides. So if I'm asked to verify, that's how I would do that. If I'm asked to evaluate an indefinite integral, then what I'm really trying to find is that antiderivative. So if I'm asked to evaluate this, it's like solving and finding out whose derivative this is. So as I work with this, I might consider rewriting this term as x to the 1/2 so that I can think about that a little bit more easily. So if I'm asked to evaluate this, I'm going to find that general antiderivative. So this is going to be 2e to the x is its own derivative, plus secant x is the antiderivative for secant x tangent x, minus 2/3 x to the 3/2, and again, spend a moment working that out, plus a constant. Pause the video and do a little catching up if you need to. So chain rule. We've mostly done things where chain rule has not been an issue, or we've practiced and dabbed a little bit into it. And what we want to do is use some U substitution the way we did when we first learned chain rule to handle nested or embedded functions. So we're going to use U to hold a place and to help us find the antiderivatives. If we use a U substitution, then we always need to do a du substitution so that we switch from either x's and dx's to u's and du's so that, again, our variable of integration matches our variable in our expression. And then if we're not sure we did it correctly, we can always take the derivative to see if we did do it correctly and get back to sine of 3x. So how can we do this? So if this is what I'm asked to integrate and find my indefinite integral, I would really like this embedded function of 3x. I know the antiderivative for sine of x, but sine of 3x would require a little bit more by chain rule. So I'm going to let that 3x be represented by u. So if I change my integral here to sine of u, I also have to change my dx then. I need my variable of integration to also be u's. And therefore, I need to go find out du dx, in other words, du with respect to x, would be 3. So in order to have a du in here, in order to get that du in there, I need 3 dx's. In order to replace and put a du in there, which I need 3 dx's, and I don't have 3 dx's in the original expression. So if I want 3 and a dx in here, that 3 was not originally part of this integral. I'll need to balance out front so that I'm not breaking any rules. Then I can go ahead and not only have my u in there still, but 3 dx's can now be replaced with du's so that I now have an indefinite integral whose variable of integration matches the variable I'm in. So now I'm going to go take my antiderivative. I'm going to integrate in terms of u's, so I've got 1/3, and that'd be negative cosine u plus constant. And therefore, my final evaluation, when I go and resub, it'll be cosine of, and again, I'm going to go put instead of u, I'm going to put my x's back, plus a constant. I need to resub. So my goal in doing this is going to be to put a u in place of that nested function or anything I realize is a composite or a composition in there. And then I need to try to rearrange so that I can see a way to get du as my variable of integration. So differentials matter. If I have a function in terms of u, I can't have my variable of integration be x's here. And that's what we're talking about with this u substitution, is I have to get that variable of integration to match. So if I'm going to do a little u substitution, your book at first is going to suggest, as they did with chain rule, what to use for u's. So they'd like me to replace u with that so that this becomes 9x squared all over the square root of u, or u to the 1/2 power, and I'm still in dx's. Knowing that my u is 1 minus x cubed, my du, derivative with respect to x, is going to be negative 3x squared. So in order to get a du as my variable of integration, I'm going to need negative 3x squared dx somewhere in my integral, in my integrand expression. So as I go to look through here, I do have the x squared right here and the dx part right there. But I don't have that negative 3 that I need. So if there's some way I could take that 9 and break it up so that instead of a 9, I could pull that apart into a negative 3 and another negative 3, things that would multiply back to being 9. I could pull one of the negative 3's out front keep one of them in here, and that would still be worth 9. A little rearrange here. And now I see everything I need in my integrand in order to replace my variable of integration and make it a du. So -3. And instead of the -3x squared dx, I'm going to be able to say 1 over u to the 1/2. And then all of those pieces make my du. When I go to evaluate, you know that I like my integrands in their exponent form. So my integrands, or my integral value then, is going to be -3. And then when I work out my antiderivative, that's going to be 2u to the 1/2 power. Oh, don't know what's going on there. Plus constant. And the last thing I have to do, and this process gets easier the more you do this, is I need to go put my u's back. So my final value is going to be -3 times that 2, my square root of 1 minus x cubed plus constant. So my final integral value will be -6 square root of 1 minus x cubed plus a constant. I've resubstituted. All right, on the next one. And again, pause the video, go back and see what else you need to work on to make this happen. U substitution is hard the first day, like most tricky things, but it gets better. So again, they've asked us to do an indefinite integral value. And my U substitution they've suggested for me, which we won't always do, but we start to get the hang of how to U substitute. So I'm going to rewrite this. So instead of all of that to the 2nd power times sine of t over, we've got a lot going on in there. My u is going to become u squared times sine of 1/2 t dt. I can't integrate right now because I need to find a way to get my du in there. If I'm going to be in terms of u, then I need du dt's that I can replace this dt somehow. And it's taking care of chain rule. So my du dt in here would be 0, and then negative cosine's derivative is going to be sine of 1/2 t with a little chain rule times a 1/2, so 1/2 sine of 1/2 a t. dt is what I need in order to get a du into that integral. And I can't have dt's in here. If I'm going to integrate in terms of u, I need du's. So looking in here, I see some of the items that I need. I see the sine of 1/2 t, I see a dt, but I don't see that extra 1/2 factor that I need. So knowing that if I double the outside, I could take and put a 1/2 multiplier on the inside so that now I have what I need to replace and get a du in there. Now I see everything in my du expression right there. This becomes the simpler integral twice u squared du. Once I've got that, then I'm going to go antiderivatives in terms of u because my variable of integration matches. So I'm looking at twice, again, don't know why it starts to do that, twice 1/3 u cubed plus a constant. But my initial function wasn't in terms of u's, so I need to do a little replacement. So 2/3 u was 1 minus cosine of t over 2 to the 3rd power plus a constant. And if you're checking and you took the derivative of this function, you'd get back to 1 minus cosine of all that. All right, we're getting close to the end here. Do 2 more u substitutions here, and I think these are a little bit easier to see where we don't suggest the u's here. I need something that if I replace u, I will be able to see u's derivative as well. So if I just make 2t plus 1 my u value here, I will not be able to just see its derivative. I will have sines and cosines in there. But if I maybe make my u something that is either sine or cosine's derivative, then I can work with that. So I'm going to make my u cosine 2t plus 1. Picking a u comes with a little experience. It's not always just your nested function. Sometimes it's one whose derivative you can still see. And so then to get a du dt in here, I would need, and again, think derivatives, I would need negative sine 2t plus 1 times, and then the nested function's derivative, a 2. So to replace a du in my expression, I'm eventually going to need a negative 2 sine 2t plus 1. All right, going back to my initial integral and doing a little u substitution. So I need the integral of, and in the denominator, I see my u value squared. In the numerator, I'm starting to see things that I will want for my du substitution as well, or replacement. Oops, I lost my dt over here, sorry. But not everything I need is in there. So I need this negative 2, and I don't see that. So again, if I want to put a negative 2 multiplied in there, I need a negative 1/2 out front to balance that, to make sure that I haven't violated the value of that indefinite integral. So my negative 1/2, now I'm seeing all the pieces I need. I'm seeing the negative 2 sine 2t plus 1 dt that I can replace. So I'm going to have 1 over u squared du, or du over u squared, some people write it. So now I'm in the same variable of integration that I am for my integrand, so u to the negative 2 du. So I'm going to have negative 1/2. Negative u to the negative 1 is my antiderivative. And I'm ready to go back and u substitute. U substitution the first time around is not that easy to do, so be patient with yourself. Instead of a negative multiplied by another negative, I'm just going to keep it positive. My 2 belongs in the denominator. My u actually belongs in the denominator because of the power that's negative on it. So that would be my final value for that integral. All right, last one. Last one, before I start to work with cotangent of 7x, I don't know an antiderivative for cotangent. So before I do anything, we've worked with changing the function before. Cotangent of 7x is equal to cosine of x over sine of x, or 7x, sorry. This might be a better integral to work with because I do see that cosine of 7x and sine of 7x have some derivatives of values in common. So I'm going to switch my integrand to an equivalent identity. And then I often pick the one in the denominator because it's easier as my u sub setup, that if I pick sine of 7x as my replacement for u, in order to get a du in there, I will need cosine 7x times 7, or 7 cosine 7x dx will be my du replacement. Whoa, okay, running out of room here. So in here, I definitely know I will have a u in the denominator. And then I'm looking to see if I can get a du by finding a cosine 7x. Got that. I've got the dx. I just need the 7. So if I multiply in here by a 7, I'd have to multiply out front by a 1/7. I can do that. So that my integrand, when I replace everything, becomes 7 cosine 7x dx is my du. I've got 1 over u du. I'm now ready to integrate because I'm in terms of u. So I've got 1/7 natural log of absolute value of u plus a constant. So my final integral value is 1/7 natural log of the sine of 7x plus a constant. So u substitution is going to take you a little bit of practice. It's going to give you suggestions on what to use for u's on some of these. On 18 through 24, please make sure that you show the work on one of them. Pick one of that set of evens, 18 to 24, to verify at least one of them, but you don't have to verify every single one. And on the syllabus page, there is a U Substitution video tutorial as well, so if you need to see more ideas and hear a different voice to work on that, you can.